Now we want to talk about the uniqueness and existence of a solution. We want to talk about Picard's theorem, which guarantees us both of these. Here's Picard's theorem. Let R be a rectangular region in the xy plane defined by A less than or equal to x less than or equal to b and C less than or equal to y less than or equal to d that contains the point x sub 0, y sub 0 in its interior. If f and the partial of f with respect to y are continuous on R, then there exists an interval I centered at x sub 0 and a unique function y of x defined on I satisfying the IVP dy dx equals f of xy and the initial condition y of x sub 0 equals y sub 0. So I've got two examples here to see, do these have unique solutions and where? So the first one, notice I have dy dx minus y equals x. Well, this is not in the form that I wanted for Picard's theorem. So what I want to do is I want to put it, first of all, in the form of Picard's theorem. So I add the y on both sides. So therefore, this is my f now. X plus y is my f. Well, I notice that x plus y is a polynomial in x, and then I've got a polynomial y. Polynomials are continuous everywhere. So f of xy is continuous everywhere on the plane. So f is continuous everywhere. Next, I need to look at the partial of f with respect to y. So I'm going to take the partial of f with respect to y, something you did in Calc 3, and I noticed the partial is 1. So notice this is a constant. So the partial is continuous everywhere. So, regardless of what my initial condition is, I see that this has a unique solution. This differential equation has a unique solution, and I'll abbreviate solution, everywhere. There's no constraints. So everywhere, and I'll put in parentheses, in the entire plane. So we remember that we're talking about R2, not R1. Now I come to this one. Y prime equal to the square root of y squared minus 9. Now I want to find out, am I guaranteed by Picard's theorem a unique solution at the point 5, 3? So the first thing I've got to decide is, what's my f? Well, my f, it's already in the nice form. My f is the square root of y squared minus 9. Let's go ahead and take the partial. The partial of f with respect to y would be, bring down the power, 1/2, raise it to the power minus 1, times the derivative of the inside. So therefore, what do I get? I get y over the square root of y squared minus 9. So now that I look at this, and I say, do I have troubles? Yes, I have troubles with this y squared minus 9, not only in the partial, but also in the function itself. If you look, where is this continuous? Well, it's only continuous when the absolute value of y is what? Greater than 3. This is in the denominator, so I can't have it equal to 3 because I can't have a 0. So less than 3 is discontinuous. Discontinuous. The absolute value of y less than 3 makes this discontinuous. Well, look at my y. My y is 3. I can't approach it. I can't even plug in 3 here. So that's less than or equal to 3. It's discontinuous. That's at 3. So this does not guarantee a unique solution by Picard's theorem. There is not guaranteed a unique solution by Picard's theorem. So we have one example where we have a guaranteed unique solution anywhere on the plane. We have this example where we're not guaranteed a unique solution, in particular at that point 5, 3.